Hi everyone, my name is Thais, and I am pursuing a master's degree in computer science at UFMG. Today, I would like to share with you a presentation of our last work, which is titled Impact of Obfuscators and Code Optimizers on the Accuracy of Program Predictors. This work is a collaboration of myself, Michael Kaneski, Vinicius Pacheco, Anderson Faustino, and Fernando Quintão. First of all, clone detection is the problem of determining whether two programs solve the same problem, even if they have a different code. And what is the importance of clone detection? In the context of computer science, we can think of malware, because the same malware can be transformed to look different, but maintain its original effect. This transformation can be used to evade an antivirus. If an antivirus has the ability to detect a clone, it can be resistant to this type of attack. Plagiarism is also a problem. Sometimes we want to find if two programs do the same thing to prevent intellectual property theft. A plagiarized program or a malware can create a transformed clone of itself via obfuscation techniques. The clone will be semantically equivalent, but will look different at an assembly level. Obfuscation techniques are responsible for making a program or system harder to understand, and consequently, the reader will be distracted to determine the true intention of the program. The obfuscator or LLVM is an example of a tool that implements three code transformations. Optimizations level, such as -03 and -01, also transforms the code and will likely make it harder to read, since their main goal is to improve performance but not legibility. Clone detection is an undecidable problem, so it's solved via conservative or statistical approaches. Pondering this subject, we raised the following research questions. There are several program representations, such as CFGs and histograms. Are there an effective representation of programs to train predictors of clones? What is the impact of obfuscation techniques on programs' performance? How effective are code obfuscations to evade predictors? And can optimizations revert to obfuscations? To answer the last two questions, we are going to use 4 games with 2 players: predictors and obfuscators. Predictors try to figure out the class or problem that a program solves. Obfuscators try to mask and make it harder to figure the real class of a program. In all games, the predictors wins if it correctly predicts the class of a program, and the obfuscators wins if it makes the predictors guess incorrectly. We are working with POJ 104, which is a collection of programs extracted from a pedagogical online judge system. POJ 104 has 104 classes of programs. Each class represents a specific problem from this judge system, and each one of these classes has 500 submissions. In Game 0, both predictors and obfuscators receive the original dataset of programs without any transformation. In Game 1, the obfuscators have the same dataset and the ability to obfuscate programs with different techniques. In Game 2, both predictors and obfuscators have the ability to obfuscate programs. Finally, in Game 3, the obfuscators can obfuscate programs, but the predictors can only optimize them. To answer the RQ1, we used the POJ 104 dataset and represented its programs with the following program representations. Each representation was used as an input to the Zenk model, which is a convolutional neural network that I discussed in our paper. We collected the accuracy of the model when trained and tested with each representation. Here, we can see our results. Histogram is a simple representation which counts the number of opcodes in a program. It consumed less than 2/5 of the memory required by CGFG, and ProgrammL, and yet it has a good result in terms of accuracy. To answer RQ2, we collected programs from the benchmark game, and we measured the speed up of these programs. But we applied different types of transformations to understand the behavior of the program when transformed. Negative bars indicate that the program is slowed down compared to its original version compiled with -0, while positive bars indicate that the program is speeded up. Optimization techniques such as -03 improve the program performance, and obfuscators don't do the same. To answer this research question, we used Game 0, Game 1, and Game 3. In all of these games, we used KNN, random forest, SVM, MLP, and logistic regression as the prediction models. And we would like to measure the accuracy of these models when they are subjected to different inputs according to the game's definitions. Here are the results of Game 0. Obfuscators have no power in this game because there is no transformation to be applied on the dataset. So the predictors need to figure the class out of the original program. Random forest was the best model with about 81% of accuracy. A random classifier would score about 0.9%. It proves that models are learning something with this data. Although SVM is a model used for binary classification, it has a strategy called one versus rest that can be used on multi-class problems. But this strategy is not so efficient. In game 1, we used the same predictors and we measured the accuracy of them. But now, the obfuscators and the predictors have access to three types of transformations. Programs are compiled using -0 and transformed using -03, MCMC, GRLSG, or OLLVM. The label OLLVM represents the combination of three transformations from the OLLVM obfuscator: bogus control flow, instruction substitution, and control flow flattening. -03 is an optimization level present in classic compilers. We used Clang from LLVM. MCMC is an abbreviation to Markov-Chain Monte Carlo, and GRLSG is an abbreviation to Deep Reinforcement Learning Sequence Generation. Both are transformations proposed by this paper, challenge machine learning-based clone detectors via semantic preserving code transformations. We compared this game with the results of Game 0, which is labeled as baseline in our chart. The OLLVM, -03, and MCMC obfuscation techniques substantially reduce the accuracy of predictors. This result also shows that optimizations can evade classifiers as well. On the other hand, naive techniques such as GRLSG does not cause the same effect. This transformation actually applies lots of small transformations in the programs, replace constants by arithmetic operations, for instance. Nevertheless, these kind of small transformations are undue when the program is transformed to a SSA format in LLVM. Now, let's see the results of Game 2, where models and predictors know the obfuscation techniques. Models in this game are able to recover their accuracy. But OLLVM is still able to hide the class of many programs. To answer this research question, RQ4, we are using game 3. Obfuscators in this game have access to obfuscation techniques, and predictors have access to optimization techniques. Predictors are not successful in undoing the transformations applied by LLVM, but MCMC and GRLSG are easily reverted, recovering the full accuracy of almost all models. From those experiments, we present the following conclusions. Histograms are as effective as complex models in the literature. Optimizations can obfuscate or normalize programs. And predictors perform better if they know the obfuscators. Thank you for your attention, and feel free to ask any questions.